So this is the astonishing, and I could go into this, a long story, but I'd rather actually get into actually calculating this stuff. But for a long time, they really weren't clear exactly what heat was. Right? They didn't understand that heat was just another form of energy. And so the chemists had heat, and the physicists had things like mgh and 1f mv² and energy and all this stuff, right? The chemists knew that heat was conserved. We knew that energy was conserved. That they were the same thing was made by, the discovery was made by Joule. He actually came up with this conversion factor. By allowing a mass to fall, he stirred a pot of water that was carefully insulated. And, well, when you do that, right, the energy of this falling weight, if it falls at a constant velocity, it's not gaining kinetic energy, so therefore the energy must be going to, well, kinetic energy of the water, right? It's stirring the water. So this is sort of a revelation to some students, is that if you turn a fan on in a closed room, if you stand in front of the fan, you might feel cooler, but the fan is actually doing what to the air? Making it go faster, yeah? It's spinning, and it's actually all the energy it does work against the air, right, is hitting the air molecules and making them go faster. Faster is hotter. Okay, so fans actually heat the air. The reason why you feel cooler is that generally, if it's not at 100% humidity, you can evaporate water off your body. Also, if you've got warmer air next to your body than the surrounding air, then it can strip that away. This is like a wind chill effect, right? But so yeah, this is an interesting thing. And in Wyoming, they've got these big wind turbines at people's houses, and they don't generate electricity and then generate heat. Some of them just generate heat by stirring a big pot of oil. They've got oil in these things, and they just stir it really fast. And if you stir the oil, it gets warm. And then you pump it through your house, and you can heat directly with wind power, which is kind of an interesting thing. So this is concept zero, is that a calorie, and what is a calorie? The amount of heat needed to raise 1 gram of water 1 degree Celsius. A kilocalorie is the amount to raise a kilogram of water 1 degree Celsius, yes. And the calories, what? That's the capital C, yeah, okay. And the calories in food, are kilocalories. Do we know that? Yeah, because like food has just a ton of energy, right? So this is our first formula, and this is MCAT, right? That heat, Q is our heat, Q is MC delta T. Okay? And Q is this is our heat. That's in joules. This is mass. And in chemistry, you did kilogram or grams. We're going to do kilograms here. Okay? Just because we don't want to change what units we use, we're going to use kilograms all throughout all this stuff, right? And then this is change in temperature. Right? And you can sort of relax. We got all excited in the ideal gas law because we were using T. We just used T, what the temperature was. And of course you had to do an absolute scale. But if you go from 20 degrees Celsius to 50 degrees Celsius, what's the difference in temperature? 30 degrees Celsius, right? What if you go from 293.15 Kelvin to 320.15 Kelvin? This is, by the way, aren't these the same temperatures just in Kelvin? So if I converted those carefully to kelvins, and then if we found the change in temperature, what would it be? Is it the same thing? Yeah, in this case, the delta T is 30 kelvins, or 30 degrees Celsius, right? A Kelvin is a degree Celsius, or something like that. Yeah, I don't know. I don't really know, but they're the same, aren't they the same? Yeah? Okay, so in this case, since you're always looking at a change in temperature, and you're never going to use what the temperature really is, it's always at how much did it change? We don't really care, right? So this is going to be degrees Celsius, but it has to be change, right? It has to be the change. And then this is the specific heat. Why do we say specific? It's specific to that substance, right? And this is in joules to raise 1 kilogram, 1 degree Celsius. So it's in joules per kilogram degrees Celsius, or as IB will enigmatically denote, kg to the -1 degrees Celsius to the -1, like that. And you just have to look those up. So now they'll start talking about stuff, and they'll say, we're going to heat up 5 kilograms of copper, right? Up until now, it's just been like a 5 kilogram mass, but now it's 5 kilograms of copper. And you're like, why are they telling me what it's made of? I've got to look it up, right? Okay. Here are some specific heats, and they are in a table in your book. Table 14.1, wherever that is in your book. So as you're doing your problems from the book, they'll say something. You'll have to go back in the book and find those things, right? So the liquid water is the hardest thing to heat up. That's why we use it in our radiators, our car radiators. A very small amount of water absorbs a lot of heat, 4,186 joules of energy, right? Ice, when you solidify water, it's easier to heat up. Why is that? I'm not exactly sure. I suppose it's because it's got fewer modes that it can store energy in. I don't know. Aluminium, easy to heat up compared to water, right? Iron. I like to say aluminium. The British way. It's the correct way. Well, there is the way the British spell it, right? Look at any other element, right? Uranium, plutonium, neptunium. Right? The British said, basically what they said is that we changed the spelling of aluminum because we couldn't pronounce it. That's kind of funny. It's probably true, too. So we don't need to actually write these down. We'll always give them to you, or they'll be in the tables. But what I do want to show you is this table here. This is kind of fun, right? Here is joules per kilogram degrees Celsius. Remember that it makes more sense to talk about stuff, though, in terms of moles. And what can you say about the moles, joules per mole degrees Celsius? What is true about those? They're way more consistent, right? And that's because these things are all of different densities or masses or something like that, right? Okay. But these guys are all pretty much in the ballpark. If you talk about a mole of stuff is just about, except one of these things doesn't go together. One of these things doesn't belong, right? Yeah, carbon. Why is carbon? Well, I don't know. Probably if I knew why this was, I'd be like a material scientist and making a lot more money. But I think the answer is that the carbon makes, these are all metals. Carbon makes these like crazy network covalent bonds. I mean, like you can't dissolve carbon with, and there's almost no type of solvent that will take like graphite out of something, right? So it's just a crazy substance. It's different from all these guys. These are metals. Carbon is a metal wannabe or something like that, right? Do I need to move you guys? Are you going to distract Brody the whole time? Don't distract him. He's just clinging to knowledge in physics. Let's try it. Get out a whiteboard. That's his first name is Albert, really. Your locker? Why would I want to see your locker?
I have a note.
Oh, the note, if I wanted to see the note. Not really. I don't think you're lying.